Hello. I'm going to go through the OCR 2022, A-Level, Chemistry, Paper 1, Periodic Table, Elements and Physical Chemistry. In the fixed comment under the video, I leave a link to my website jctnotes.com where you can see the written answers to this paper. We start with Section A, Question 1. An aqueous solution contains a mixture of chloride, bromide, and iodide ions. Silver nitrate is added to this mixture, followed by an excess of dilute ammonia. The resulting mixture is then filtered. Which compound or compounds are present in the residue on the filter paper? This is the classic identification of halides in solution. All of them precipitate with silver nitrate, typically in acid medium. Addition of excess of dilute ammonia dissolves the silver chloride. Addition of excess of concentrate ammonia dissolves the silver chloride and the silver bromide. In this question, we are going to dissolve the silver chloride only, leaving silver bromide and silver iodide. The answer is D. In question 2, 20 cubic centimeters of nitrogen gas reacts with 10 cubic centimeters of oxygen gas to form 20 cubic centimeters of a gaseous product. We are asked to choose the equation most likely for the reaction from 4 possible equations. The proportions in the given volumes indicates the proportions in the number of mole of the different components in the reaction. We can think, 2 mole of nitrogen gas reacts with 1 mole of oxygen gas to form 2 mole of a gaseous product. This proportion is only obtained in answer C. In question 3, 0.541 grams of an element X is reacted with oxygen to form 0.790 grams of the oxide X2O3. What is the element X? Aluminium, chromium, gallium, or scandium? The mass of oxygen used is 0.790, take away 0.541 equals to 0.249 grams of oxygen. With the molecular mass of oxygen, we can find that it is equivalent to 7.781 multiplied by 10 to the power of minus 3 mole of oxygen. The adjusted reaction that we are looking at, is 4 mole of element X react with 3 mole of oxygen to form 2 mole of compound X2O3. The proportion between X and oxygen is 4 to 3. With the number of moles of oxygen that we have, we can see that the number of mole of X that we have is 1.0347 multiplied by 10 to the power of minus 2 mole of X. With this number of mole of X and the mass used, we can find its atomic mass is 52.14 grams per mole. Looking at the periodic table from the data sheet, we find that this match with the chromium, with atomic mass of 52, allowing some margin for rounding errors. Therefore, the answer is B. In question 4, we have the reaction of the oxidation of hydrogen peroxide with manganate 7 ions under acid conditions. In a titration, 25 cubic centimeters of a disinfectant containing hydrogen peroxide reacts with 22 cubic centimeters of 0.125 molar potassium permanganate. We are asked what is the molar concentration of hydrogen peroxide in the disinfectant. We assume that the permanganate only reacts with hydrogen peroxide in the disinfectant. Multiplying the volume of potassium permanganate by its molar concentration, we get 2.75 multiplied by the 10 to the power of minus 3 mole of potassium permanganate. From the stoichiometry of the equation, we know that 2 mole of potassium permanganate react with 5 mole of hydrogen peroxide. Therefore, the 2.75 multiplied by the 10 to the power of minus 3 mole of potassium permanganate that we have, react with 6.875 multiplied by the 10 to the power of minus 3 mole of hydrogen peroxide. As these were in 25 cubic centimeters, or 0.025 cubic decimeters, the concentration is 0.275 molar. The answer is C. In question 5, we are given the mass of 4 molecules of a substance. We are asked to identify the substance from 4 possible options. If we divide the mass by 4, we get the mass per molecule. If we multiply this number by Avogadro number, we get the molecular mass of the substance as 31.98 grams per mole. If we compare the molecular mass of the answers, we have methane, 16 grams per mole. Oxygen, 32 grams per mole. Sulfur dioxide, 64 grams per mole. Iodine, 254 grams per mole. We can see that the 4 molecules are made of oxygen. Answer is B. In question 6, we have the formula of Prussian blue. It is made of iron plus 2, iron plus 3 and cyanide minus 1 ions. We need to find the numbers of iron plus 2 and iron plus 3, in one formula unit of Prussian blue. From the formula, we know that there are 18 cyanide minus 1 ions, therefore the iron 2 and the iron 3 ions need to neutralize these 18 negative charges. We just need to check what will be net charge of the difference answers. Option A gives 19 positive charges. Option B gives 18 positive charges. Option C gives 17 positive charges. Option D gives 16 positive charges. Therefore, the answer is B. In question 7, we are given a table with bond enthalpies and we are asked to calculate the enthalpy change in the given reaction. Based on the definition of bond enthalpy, it is the energy needed to break 1 mole of a particular bond in 1 mole of gaseous molecules. The answer is straightforward. We need to calculate the energy required to break all the bonds broken in reactants and add the energy produced when all the bonds of the products are formed. Careful with the signs of the energy, as the definition of bond enthalpy refers to break of bonds. In the reactants, where we calculate the breakage of bonds, we use the given values, that is positive values, but in the products, where we calculate the formation of bonds, we need to change the sign, that is to use them as negative values. Let's start with the reactants. The methane has 4 carbon-hydrogen bonds, with 435 kilojoules each. It contributes with 1740 kilojoules. Each oxygen has a double oxygen-oxygen bond with a value of 498 kilojoules per mole. 2 oxygens provide 996 kilojoules. We continue with the products. Remember that we need to change the signs from those provided. Each carbon dioxide has 2 single carbon-oxygen bond, giving 2 times minus 805 equals to minus 1610 kilojoules. Each water molecule has 2 oxygen-hydrogen bond, each with a contribution of minus 464 kilojoules. The total contribution of the 2 moles of water is 2 times minus 464 equals to minus 1856. Adding all together, we get minus 730. The answer is A. In question 8, we are asked for the rate constant of a first-order reaction with half-life of 80 seconds. For a first-order reaction, we have that the constant K is equals to the Neperian logarithm of 2 divided by the half-life. Replacing values, we get 8.66 by 10 to the power of minus 3. The answer is A. In question 9, we are asked which of the 4 provided equations represents the change that accompanies the standard enthalpy change of atomization of bromine. By definition, the standard enthalpy change of atomization is the enthalpy change when 1 mole of gaseous atoms is formed from its element under standard conditions. Answers B and D refer to 2 mole of gases, they are discarded. The bromide in standard conditions is a liquid, therefore only answer A is the correct one. In question 10, we are asked what are the signs of change of enthalpy and entropy for the condensation of ammonia gas. Condensation, Change from a gas phase to a liquid phase is exothermic. We need to remove heat from the system to transform from a gas to a liquid, therefore change of enthalpy is negative. Option C and D are discarded. From gas to liquid we are moving to a more ordered system, thus change of entropy is also negative. Option A is the only option. The correct answer is A. In question 11, we are given the equilibrium equation for an indicator, HA. In the form HA, the indicator is blue, but when it is dissociated as a minus and H+, it is yellow. The indicator is added to a solution. The indicator turns a yellow color. An excess of aqueous sodium hydroxide is then added. Which of the four statements provided describes how the color of the solution would be expected to change? As the indicator turns yellow when added to the solution, we are in the dissociated form. The addition of sodium hydroxide will remove protons from the system and the equilibrium will be displaced to the right, Le Chatelier's principle, favoring the formation of yellow color. This means that the color stays yellow. The answer is D. In question 12, we are dealing with the ammonia and water acid-base equilibrium. We are asked what are the Bronsted-Lowry acids in the equilibrium mixture. A Bronsted-Lowry acid is a proton donor. The reaction of ammonia with water is. In this equilibrium we have two substances that donate protons. On the left-hand side water donates protons to the ammonia. On the right-hand side the ammonium ion, NH4+, donate protons to the hydroxyl ion, OH-. So, the acids are ammonium ion and water. Therefore, the answer is C. Question 13 was cancelled from the exam. In question 14, we are given three reactions, each reaction form one product only. We are asked which reaction or reactions form a product with nonpolar molecules. In reaction 1, we obtain carbon dioxide, a linear molecule that is nonpolar. In reaction 2, we obtain silicon tetrachloride, a tetrahedral molecule that is also nonpolar. In reaction 3, we obtain sulfur hexafluoride, a octahedron molecule with 90 degrees fluor or sulfur fluor angles, and it is also a nonpolar molecule. Consequently, reactions 1, 2 and 3 form nonpolar products and the answer is A. In question 15, we are asked which ion or ions contain one or more unpaired electrons, manganese 3+, vanadium 3+, and copper+. All these are metals from the first series of the transition metals. The valence electrons are from the orbitals 3d and 4s. When these metals are ionized, they tend to lose first the electrons in the orbital 4s before the orbitals 3d, that is the reason that I put the orbital 4s at the end. In the manganese metal, we have the configuration 3d5, 4s2. When it loses 3 electrons to form the ion manganese 3+, it loses 2 electrons in the orbital 4s and 1 electron from an orbital 3d, leaving a total of 4 unpaired electrons in the orbitals 3d. Vanadium has an electronic configuration 3d3, 4s2. To form the ion vanadium 3+, it loses the 2 electrons on the orbital 4s and 1 electron from an orbital 3d, leaving 2 unpaired electrons in 3d. The copper atoms also have just 1 electron in the orbital 4s, the remaining 10 electrons are arranged in the orbitals 3d, each filled by 2 electrons. This configuration is more stable, as half-filled or completely filled orbitals are more stable than those filled with 1 electron less, and the atom will transfer 1 electron from the orbital 4s to the 3d. When ion copper 1+ is formed, the electron in the orbital 4s is lost, leaving all the 10 electrons paired in the orbitals 3d. Therefore, manganese 3+ and vanadium 3+ have 1 or more unpaired electrons and the copper 1+ has all the electrons paired. The answer is B. We starts the section B of the exam. Question 16 is about a catalytic converter that removes nitrogen monoxide and carbon monoxide from the exhaust gases in a car. In part A, we are given a reaction of the catalyst converter, and we have two questions. In the first question, we need to explain how increasing the temperature increases the rate of the given reaction. We are provided with a grid to sketch a labeled Boltzmann distribution. The Boltzmann distribution is a graph of the number of molecules plotted against the kinetic energy of the particles. I have drawn my graph. Any graph would be acceptable as long as: first, the curves start near or at the origin. Second, they do not touch the x-axis at high energy. Third, it is clear which curve correspond to the highest temperature. Fourth, the maximum of the curve for higher temperature must be to the right and lower than the maximum of the curve for lower temperature. Fifth, lines can only cross once. The explanation is that at higher temperatures, more molecules have energy higher than the activation energy, allowing to have more effective collisions. In the second question of part A, question 16, we carry on working with the same equation. The rate of equation has been investigated performing 3 experiments given in a table. We are asked to determine the orders with respect to nitrogen monoxide, NO, and carbon monoxide, CO, the rate equation and the rate constant, K, including units, explaining our reasoning. We can assume that the rate is going to have the general form where the rate equals to the constant K multiplied by the molar concentrations of nitrogen monoxide and carbon monoxide, each to the power of a constant, that we will call A, for the nitrogen monoxide and B, for the carbon monoxide. The first step is to find the orders with respect to NO and CO, A, and B respectively. We start by comparing the different experiments, looking for relationships between concentrations and use these numbers to find A and B. Comparing experiments 1 and 2, we see that the concentration of carbon monoxide is constant, and when we double the concentration of nitrogen monoxide the initial rate increase by 4. We can conclude that the order to NO is 2. Sometimes is not easy to see this, and we can take a more systematic approach. We are still with experiment 1 and 2. Replacing in the equation of the rate the values obtained in the analysis we have. If we divide experiment 2 by experiment 1, cancelling common terms and simplifying, we find that A equals 2. We clear the work that we done so far and replace A equals 2 in the equation. We now compare experiments 2 and 3. You can follow a reasoning similar to the comparison between experiments 1 and 2, as I have done on my website, but I find easier to explain using the systematic approach of using the rate of equation. This method is also less prone to errors in the exam. Replacing the values that we have in the rate equation. If we divide experiment 3 by experiment 2 and simplify, we can see that B equals 1. I put all the numbers in one go to speed the process. We have now the order respect to NO and CO. To find the rate constant we replace the values obtained in any of the experiments, for example, using experiment 1, and we get where we can find that the value of the rate constant is 3.374 times 10 to the power of 6. To find the units, we know that rate units are mole per decimeter and second, and the concentrations are mole per decimeter. Replacing these units in the equation of the rate, we find that K have the units of cubic decimeter to the power of 6 multiply by mole to power of -2 and multiply by seconds to the power of -1. And with this, we answered the question. In question 16b, we are given another equation between carbon monoxide and nitrogen dioxide and its rate of reaction. We are asked by a possible two-steps mechanism for the given reaction, with the first step much slower than the second step. What we need to cover in the answer is: first, in the initial step, the slow step, we are going to need 2 molecules of nitrogen dioxide as reactant because the rate only depends on nitrogen dioxide and it is of order 2. Second, whatever intermediate species that we create in the step 1, will need to disappear in step 2. Third, if we add step 1 and step 2, we should get reaction 16.2, no additional or missing species. There are several possible solutions. I copy here the examples given in the marking scheme. Question 17 is about energy changes. Part A is about the reaction of magnesium with aqueous silver nitrate. We are given the reaction and the enthalpy changed associated with it. A student adds an excess of magnesium to 100 cubic centimeters of 0.4 molar silver nitrate solution. The initial temperature is 20 degrees centigrade. In the first question, we are asked to determine the maximum temperature reached in this reaction, giving the answer to 3 significant figures. We assume that the specific heat capacity and density of the solution are the same as for water, and that there are no heat losses. As we have excess of magnesium, the limiting reactant is silver nitrate. As the enthalpy given is in kilojoules per mole, we need to calculate the number of mole of the limiting reactant. We can get it by multiplying the concentration by the volume used, making all the necessary unit changes required. I get 0.04 mole of silver nitrate. From the reaction, we get 678 kilojoules, or 678,000 joules per 2 mole of silver nitrate. 0.04 mole of silver nitrate provides 1,356 joules. As the solution has a volume of 100 cubic centimeters and we are taken its density as the water, we can consider that the mass of solution is 100 grams. The energy supplied to the system is going to be used to increase the temperature of the system. This energy is equals to the mass of the solution multiplied by the specific heat of the water, 4.18, and the increase in temperature. I get that the increase in temperature is 32.44 degrees centigrade. As the initial temperature was 20 degrees centigrade, an increase of 32.44 degrees will lead to 52.44, or 52.4 to 3 significant figures. We continue in question 17, part A. In the second question, the student repeat the experiment, adding an excess of magnesium to 50 cubic centimeters of a 0.4 molar silver nitrate. We are asked to predict, with reasons, how this modification would affect the maximum temperature reached, assuming that there are no heat losses. The temperature should be the same as we are using half of the silver nitrate to increase the temperature of half of the solution. Still in question 17, we move to part B. We are given the equation and the enthalpy of the first stage in the process to manufacture nitric acid from ammonia in a multi-stage process. We are also given the enthalpy change of formation of ammonia and water in a table. We have 2 questions. In the first question, we are asked to explain the term enthalpy change of formation. In the second question, we are asked to calculate the standard enthalpy change of formation of nitrogen monoxide. For the first question, enthalpy change of formation is the change of enthalpy when 1 mole of a compound is formed from its pure elements. For the second question, we will use the Hess's law and write that the change of enthalpy of the reaction is the sum of the enthalpy of formation of the products minus the sum of the enthalpy of formation of the reactants. We replace the numbers that we have, bearing in mind that the enthalpy of formation of the oxygen is 0 because this is the reference state of the oxygen. If we made the enthalpy of formation of the nitrogen monoxide the subject, we get that its value is 90 kilojoules per mole. We continue with question 17, part C. We are given the reaction of carbon disulfide to react with dinitrogen oxide and the entropies of the species involved in the reaction. We are asked 3 questions. In the first question, we are asked to explain the term entropy. Entropy is a measure of disorder or the dispersal of energy within a system. In the second question, we are given the free energy change of the reaction at 25 degrees centigrade. We are asked to calculate the enthalpy. The enthalpy can be calculated by the relation that increase in free energy is equals to increase in enthalpy minus the product of the absolute temperature and the entropy. We have the free energy and the temperature. The change in entropy can be calculated by adding the entropy of the products and take away the entropy of all the reactants. If we replace the data given in the equation, we get a value of 0.284 kilojoules per Kelvin and mole. We now have all the data to calculate the enthalpy. Remember that the temperature is in Kelvin. I get a value of -2587.368 kilojoules per Kelvin and mole. In the answer, I round to -2587. In the third question, we are asked if the affirmation that reaction 17.2 is feasible at all temperatures is correct or not. A reaction is feasible if the change of free energy is negative or zero. The free energy is the difference between change of enthalpy minus the product of the absolute temperature and the change of entropy. The enthalpy is negative. Absolute temperature and entropy are positive, so its product is also positive. We finish subtracting a positive number to a negative number, making the number more negative. The change of free energy is, therefore, negative and the reaction is feasible. The student is correct. In question 18, we have the graph showing the first ionization energies for elements from helium to boron in the periodic table. In section A, we are asked to complete the table for carbon, nitrogen, oxygen, fluor, and neon. The definition of the first ionization energy of an element is the energy needed to remove one electron from each atom in 1 mole of atoms of the element in the gaseous state to form 1 mole of gaseous 1+ ions. With the exception of helium, all the elements given are from the second period of the periodic table and ordered in increasing atomic number. We can estimate the approximate values if we use our knowledge of chemistry. First, the first ionization energy will increase with atomic number, as the charge of the nucleus increases and attract more the electron. Second, there is going to be a small decrease between the nitrogen and the oxygen because the nitrogen have the 3 orbitals 2p half filled and the oxygen has a 2p orbitals with a pair of electrons, being more stable the configuration of the nitrogen than the oxygen. Third, the neon should have lower energy than the helium, as there is an effect of shielding from the electrons to the electron that is going to be removed. My answer with these points would be something like this. In question B, we are asked to estimate the energy required to form 1 ion lithium plus 1 from 1 atom of lithium. We need the answer in kilojoules and to 2 significant figures. From the graph, we can estimate that for 1 mole of lithium gas, we need 500 kilojoules per mole. As the question refer to 1 atom, we need to divide by the Avogadro number. Rounded to 2 significant figures, I get 8.3 by 10 to the power of -22. In question 18c, we are asked to explain why the first ionization energies of helium and beryllium are both higher than the first ionization energy of lithium. In the case of helium, it is completing its first electronic shell 1s, the electron of lithium is in the orbital 2s, subjected to shielding from the inner shell of electrons. Helium electrons experience greater nuclear attraction. In the case of beryllium, the shielding effect due to electrons form 1s is similar to lithium, but there is an increase in the nuclear charge, giving greater attraction to the electron to be removed. In question 18d, we need to explain why the first ionization energy of beryllium is higher than the first ionization energy of boron. The beryllium has an electronic configuration of 1s2, 2s2, and the boron, 1s2, 2s2, 2p1, and electrons in 2p have higher energy than electrons in 2s, making it easier to remove. Question 19 is about acids and buffer solutions. Part A deals with the titration of succinic acid with potassium hydroxide as per the given equation. The succinic acid is taken from succinic acid health supplements. The procedure is: Stage 1, 4 tablets of the health supplement are crushed and dissolved in distilled water. Stage 2, the solution is diluted to 250 cubic centimeters in a volumetric flask. Stage 3, the student titrates 10 cubic centimeters portions of the solution obtained in stage 2 with 0.06 molar potassium hydroxide, using phenolphthalein as the indicator. We are provided with a table of a trial titration followed by 3 further titrations. In question 1 of this section, we are asked to complete the table and calculate the mean titer to be used to analyze the results. The last row is filled by subtracting the values of the initial reading to the value obtained in the final reading. The mean titer is calculated from concordant results within 0.1 cubic centimeters of each other, and the trial is not included. It doesn't matter how good it is. Concordant results are trials 1 and 3. The average titer is 22.50 cubic centimeters. In the second question of Part A, of question 19, we are asked to calculate the mass, in milligrams and 3 significant figures, of succinic acid in 1 tablet of the health supplement. I copy here the data from the problem that we need. The number of mole of 0.06 molar potassium hydroxide used in the 22.50 cubic centimeters used in the titration is 1.35 by 10 to the power of -3. From the equation of the reaction, we know that 1 mole of succinic acid reacts with 2 moles of potassium hydroxide. So, we have neutralized 6.75 by 10 to the power of -4 mole of succinic acid. These were taken from 10 cubic centimeters portions from 250 cubic centimeters. We can calculate that in the 250 cubic centimeters solution we have 0.016875 mole succinic acid. Calculation of the molar mass of succinic acid gives us a value of 118 grams per mole. With this value, we can find that the mass of succinic acid that we have is 1.99125 grams. These were provided by 4 tablets. Thus, each tablet provided 0.4978 grams. That, expressed in milligrams and rounded to 3 significant figures, is 498. Question 19, Part B, deals with glycolic acid. We are given the pKa of the acid. A buffer solution is prepared by adding 60 cubic centimeters of 0.750 molar glycolic acid to 40 cubic centimeters 0.625 molar potassium hydroxide. In the first question, we are asked to explain why a buffer solution is formed. A buffer solution is a solution in which the pH does not change significantly when small amounts of acids or alkalis are added. With glycolic acid in excess, the addition of potassium hydroxide forms the conjugate salt, potassium glycolate, and small amount of acid or alkali will not change the equilibrium much, keeping the pH constant. In the second question, we are asked to calculate the pH of the buffer solution, giving the answer to 2 decimal places. With the glycolic acid in excess, all the potassium hydroxide will be consumed, leaving in the solution glycolic acid and glycolate, that form the equilibrium. Now, we need to find the initial concentrations, the change in concentrations and the concentrations in equilibrium of the different species of the equilibrium. As we are mixing 60 cubic centimeters of glycolic acid with 40 cubic centimeters of potassium hydroxide, assuming that the volumes are additive, the final volume that we have is 100 cubic centimeters, or 0.1 cubic decimeters. As we start with 60 cubic centimeters of 0.75 molar glycolic acid, we start with 0.045 mole glycolic acid. These have been diluted to 0.1 cubic decimeters, therefore its initial concentration is 0.45 molar. I add this number in the table. For calculation purposes, we consider that we start with 0 glycolate and 0 protons. We now check the change when we add the potassium hydroxide. As we are adding 40 cubic centimeters of a 0.625 molar solution, we can calculate that we are adding 0.025 moles. As these are diluted to 0.1 cubic decimeters, the concentration of potassium hydroxide that we have added is 0.25 molar. All this potassium hydroxide has reacted with the glycolic acid to form the glycolate in the solution. So in the table I add plus 0.25 in the glycolate and minus 0.25 in the glycolic acid. We don't have data for the protons, so I put X. We now calculate the concentrations in equilibrium, by adding the two previous rows. We are making the approach that, as the acid is a weak acid, the value of X is much lower than 0.20. If this was not the case, we will need to use the concentrations put in the red note and work in the same way, but this will result in a quadratic equation. Using the expression of the dissociation constant, we can find that the concentration of protons is 1.183 by 10 to the power of minus 4. This value is much lower than 0.20 and therefore the approach is acceptable. Taking logarithm, we find that the pH is equals to 3.926. Rounded to 2 decimal places, pH equals to 3.93. The last question in question 19, part B, a small amount of aqueous ammonia is added to the buffer solution. We are asked to explain, in terms of equilibrium, how the buffer solution would respond to the added ammonia. The ammonia, an alkali, will react with the protons, forming ion ammonium and will displace the equilibrium glycolic acid glycolate to the right. Question 20 is about equilibria involving hydrogen. Question A, is the industrial use of hydrogen to manufacture ammonia based on the given equation. 1.20 mole of nitrogen is mixed with 3.60 mole of hydrogen in a 8 cubic decimeter container. The mixture is heated to 550 degrees Celsius with an iron catalyst and allowed to reach equilibrium. The equilibrium mixture contains 0.160 mole of ammonia. We are asked to determine the equilibrium constant and explain why the operational conditions used by industry may be different from those required for a maximum equilibrium yield of ammonia. We start by calculating the number of moles in equilibrium for the species involved in the reaction. From the given data, we start with 1.20 mole of nitrogen, 3.60 of hydrogen and none of ammonia. We check now the change of the different species in the reaction. We know that in equilibrium we have 0.160 mole of ammonia, thus, the change in ammonia is plus 0.160 mole. From the stoichiometry of the reaction, we know that 1 mole of nitrogen produces 2 mole of ammonia. As in equilibrium we have 0.16 mole of ammonia, we are going to reduce the number of mole of nitrogen by 0.08. Similarly for the hydrogen, from the stoichiometry of the reaction, we know that 3 moles of hydrogen produces 2 mole of ammonia. As in equilibrium we have 0.16 mole of ammonia, we are going to reduce the number of mole of hydrogen by 0.24. We can complete the table with the number of moles in equilibrium. For nitrogen we started with 1.20, reduced the concentration by 0.08, we have in equilibrium 1.12 moles of nitrogen. For hydrogen we started with 3.60, reduced the concentration by 0.24, we have in equilibrium 3.36 moles of hydrogen. To calculate the value of equilibrium constant, we divide the number of moles of each species by the final volume of 8 cubic decimeters. we get molar concentrations of 0.14 for nitrogen, 0.42 for hydrogen and 0.02 for ammonia. Replacing these values in the equilibrium constant, we get a value of Kc equals to 0.0386. Working with the units, we get units of decimeter cubic to the power of 6 multiply by mole to the power of -2. To finish part A of question 20, we need to explain why the operational conditions used by industry may be different from those required for a maximum equilibrium yield of ammonia. We start for checking what operational conditions are given to elaborate the answer. We are given information about temperature and a negative enthalpy that indicates that it is exothermic reaction. Therefore, we need to talk about temperature. We are given details about the volume and the species in the reactions are all gases. This indicate that we need refer to the volume or the pressure. We finally have a mention to the catalyst. We need to address this topic in the answer. My answer would be something like: effect of pressure, an increase in pressure will displace the equilibrium to the right, as there are less mole of gases on the right hand side. Le Chatelier's principle, higher pressure will also increase the yield, as more molecules will collide. However, working at high pressures might be unsafe and precautions should be taken to minimize risks, and high pressure is expensive to generate. Effect of temperature, as the reaction is exothermic, an increase of temperature will displace the equilibrium to the left, Le Chatelier's principle, but also increase the rate of collisions between molecules, increasing the yield. A compromise temperature should be found between these two competing effects. The catalyst increases the rate of collisions by reducing the activation energy and helps to reduce the temperature required for the process. The catalyst does not affect the equilibrium, just allow to reach it faster. The conditions used in the industry are usually a compromise between reducing costs and increasing productivity. Part B of question 20 deals with the use of hydrogen to reduce the iron oxide as per the reaction shown in equilibrium 20.2. The reaction is carried out at 500 degrees Celsius. The first question says that when the temperature is decreased, the value of Kp decreases. We are asked to determine whether the forward reaction is exothermic or endothermic. The value of Kp for this reaction is given by the partial pressure of water vapor to the power of 4 divided by the partial pressure of the hydrogen to the power of 4. As increase in temperature decreases the value of Kp, this is an indication that the partial pressure of the water vapor decreases and the partial pressure of the hydrogen increases. The equilibrium is displaced to the left, the forward reaction is endothermic. In the second question, we have a statement from student 1 saying there are more moles of products than reactants, so increasing the pressure will shift the equilibrium to the left-hand side. However, student 2 disagrees. We are asked to determine which student is correct. Student 2 is correct. The pressure only affects to the gases. In equilibrium 20.2 there are the same number of mole of gases in both sides of the equation, therefore the pressure will not have an effect. Question 21 is about the reactions of group 2 metals and their compounds. In part A, a student adds magnesium to dilute hydrochloric acid in one test tube. The student adds calcium to dilute hydrochloric acid in a second test tube. A redox reaction takes place in each test tube. In the first question we are asked to suggest 2 observations from the student's experiment that would show that calcium is more reactive than magnesium. The general reaction when the metals of the group 2 reacts with dilute hydrochloric acid is to produce the relevant chloride salt and producing bubbles of hydrogen gas. The student would observe that: first, the calcium forms more bubbles faster than the magnesium. Second, the calcium dissolves faster than the magnesium. In the second question, We are asked to write half equations for the reaction of magnesium with hydrochloric acid. The reaction that we have between the magnesium and the hydrochloric acid is the formation of magnesium chloride and hydrogen. We know that the oxidation states of the magnesium and the hydrogen are zero, as they are elements on their natural state. We can see that the magnesium changes from state 0 to state +2 in the magnesium chloride, meaning that it has lost 2 electrons. On the other hand, the hydrogen starts with oxidation state +1 in the hydrochloric acid and finish with oxidation state 0, this means that it has gained 1 electron. We can then conclude that, the oxidation half equation is, metallic magnesium forms magnesium 2+ and loses 2 electrons. Reduction half equation, 2 protons gain 2 electrons and form hydrogen gas. I find helpful the mnemotechnic oil rig, for oxidation is losing and reduction is gaining. In part B of question 21, a sample of barium oxide is added to distilled water at 25 degrees Celsius. A colorless solution forms containing barium hydroxide. The solution is made up to 250 cubic centimeters with distilled water. The pH of this solution is 13.12. In the first question, we are asked to determine the mass of barium oxide used, giving the answer to 3 significant figures. The reaction that we have is that the barium oxide reacts with water to form barium hydroxide. As this is a strong base, we can consider that it is completely dissociated. As the pH equals to 13.12, we can find that the pOH equals to 14 minus 13.12 equals to 0.88. And the concentration of hydroxyl is 10 to the power of minus pOH, that is 0.1318 molar. As the final volume of the solution is 250 cubic centimeters, or 0.25 cubic decimeters, the number of mole of OH is 0.03295. From the stoichiometry we have that 2 mole of OH are produced per mole of barium oxide, the number of mole of barium oxide is 0.016475. We can calculate the molecular mass of barium oxide is 153.3 grams per mole. And find that the mass of barium oxide is 2.5256 grams. Expressed in 3 significant figures is 2.53 grams. In the second question, 10 cubic centimeters of dilute sulfuric acid is added to 10 cubic centimeters of the colorless solution of barium hydroxide. We are asked to write an ionic equation, including state symbols, for the reaction. This is a typical neutralization reaction between an acid and base. We have also to bear in mind that the sulfates of the group 2 tend to be insoluble in aqueous solution and precipitate. Magnesium sulfate is an exception, as it is soluble in water. The reaction that we have is. Remember that they ask for the ionic equation, therefore we need to state the ions. Part C of question 21 is about limestone and huntite, 2 calcium minerals. In the first question, we have a sample of limestone contains 95% by mass of calcium carbonate. We also have fertilizer Z, with the formula and relative molecular mass provided. We need to calculate the mass, in grams, of limestone needed to make 1.5 kilograms of fertilizer Z, giving the answer to 3 significant figures. Using the relative atomic mass of the fertilizer, we can find that 1.5 kilograms, or 1,500 grams, is 1.388246 mole. At the moment, I'm using 6 decimal places to minimize rounding errors. From the formula of fertilizer Z, we can see that for each mole of fertilizer we have 5 moles of calcium. Each mole of calcium carbonate have 1 mole of calcium. Then, for 1 mole of fertilizer Z, we need 5 mole of calcium carbonate. And for 1.388246 mole of fertilizer, we need 6.942 231 mole of calcium carbonate. Using the relative molecular mass of the calcium carbonate 100.1 grams per mole, we find that we need 694.817 grams of calcium carbonate. As the limestone contains 95% by mass of calcium carbonate, we need 731.386 grams of limestone. To three significant figures, 731 grams. The second question of this part, we are asked to construct the equation for the reaction of huntite with dilute hydrochloric acid to produce bubbles of a gas and a colorless solution. We are given the formula of huntite. We need to include state symbols. Carbonates of the group 2 react with acids to produce salt, water, and carbon dioxide gas. We need to adjust the equation. We start by fixing the number of mole of huntite to 1. Huntite provides all the magnesium, the calcium, the carbon, and the oxygen to the products, so we can adjust these atoms in the products. In particular, we have 3 mole of magnesium, 1 mole of calcium, 4 mole of carbon, and 4 times 3 equals to 12 mole of oxygen. The only molecule left to adjust is the hydrochloric acid that can be adjusted by counting the hydrogen and the chloride. We need 8 mole of hydrochloric acid, and we finish by adding the state symbols. Question 22 is about reactions of transition metal compounds. In part A, we are provided with the structure of the ethane 1,2-diamine. In the first question, we are asked to explain why ethane 1,2-diamine can act as a bidentate ligand. The amine group presents a pair of electrons that can donate to an ion or a metal and form a dative covalent bond. As the ethane 1,2-diamine has 2 amine groups at each extreme, it can form 2 dative covalent bonds. In the second question of part A, from question 22, we have that the iron 3 ion forms a complex ion with 2 ethane 1,2-diamine ligands and 2 chloride ligands. This complex ion has cis and trans stereoisomers, and one of these stereoisomers exists as optical isomers. We are asked to determine the empirical formula, with charge, of the complex ion and draw the 3D structures of the 3 stereoisomers. Let's start with the empirical formula. This is going to be formed by 1 ions iron 3 plus 2 chloride ligands, they usually acts as ion chlorine minus 2 molecules of 2 ethane 1,2-diamine. The empirical formula of each ethane 1,2-diamine molecule is 2 atoms of carbon, 8 atoms of hydrogen, and 2 atoms of nitrogen. 2 molecules of ethane 1,2-diamine molecule will double these amounts. Adding all together, we have 1 atom of iron, 2 of chlorine, 4 atoms of carbon and nitrogen, and 16 of hydrogen, written in any order. The charge is 3 positive from the iron and 2 negative from both chlorine ions, giving a total net charge of 1 positive. We move to the structures. The iron 3 plus is going to have a coordination number of 6. 1 for each of the 2 chlorine ions and 2 for each of the 2 ethane 1,2-diamine. With coordination 6, we expect to have an octahedral shape. We also expect to have 3 isomers. We know that. First, there is going to be cis isomers, 2 identical ligands are adjacent to each other, and trans isomers, 2 identical ligands are opposite each other. Second, as one of these isomers is going to exist as optical isomers, we know that they are going to be 2 specular images. With this information, we need to draw the structures. These will not be unique. The example solutions given in the mark scheme are. Whatever structure you draw, make sure that first, in the cis isomer, you have 2 identical ligands are adjacent to each other, and draw one of them as specular image of the other, generating optical isomers. Second, in the trans isomer you have the 2 identical ligands opposite each other. In this case, there is no specular image. In part B of question 22, we have aqueous sodium hydroxide added to an aqueous solution of iron 2 sulfate. A pale green precipitate forms which turns brown when left to stand in air. We have two questions. In the first question, we are asked to write an ionic equation for the formation of the pale green precipitate. Note, next question give a clue of what is going on. I leave a link in the description where you can find a link to the color of precipitates from OCR. Try to learn it for the exam and have it handy in your exam preparation. The green precipitate is iron 2 hydroxide. The ionic equation for the reaction is. In the second question, we are given a table with electrode potentials and we are asked, using the information from the table, to explain why the pale green precipitate turns brown when left to stand in air and construct an equation for the reaction which occurs. Oxidation of iron hydroxide 2 with air produces brown iron 3 hydroxide. From the given table, we can see that the redox system 2 is more positive than redox system 1, and this reaction will be favored to occur. If we reverse the redox system 1 and the potential we have to have the same number of electrons on both redox equations, we multiply the first one by 4. If we add both reactions, we get eliminating common terms and adding potentials. With a potential equals to 0.96 volts, this reaction will be favored in the forward direction. This shows that the green iron 2 hydroxide is oxidized to brown iron 3 hydroxide. In part C of question 22, is about copper and copper compounds. 3 experiments have been performed. In experiment 1, hydrochloric acid is added to an aqueous solution containing aqueous copper 2 complex ions. A yellow-green solution forms containing complex ion B. In experiment 2, a piece of copper metal is heated with concentrated sulfuric acid. A reaction takes place forming a pale blue solution C and 45 cubic centimeters of a gas D, measured at room temperature and pressure. The mass of gas D is 0.12 grams. In experiment 3, an excess of copper 2 oxide is heated with dilute nitric acid. The resulting mixture is filtered. The filtrate is a blue solution A. Aqueous potassium iodide is added to the blue solution A. A white precipitate F and a brown solution G form. We are asked to determine the formulae of the species B to G and construct equations for the reactions taking place, including any changes in oxidation number. As I mentioned in the part B of question 22, I leave a link in the description where you can find a link to the color of precipitates from OCR. Try to learn it for the exam and have it handy in your exam preparation. In experiment 1, the addition of hydrochloric acid to an aqueous solution containing aqueous copper 2 complex ions produces the complex B, tetrachlorodocuprate 2-. In experiment 2, we start with the gas D, that at room temperature and pressure has a volume of 45 cubic centimeters. Using the general gas equation, we know that a mole of gas in these conditions occupy 24 cubic decimeters, or 24,000 cubic centimeters. Therefore, the 45 cubic centimeters is 1.875 by 10 to the power of -3 mole. As its weight is 0.12 grams, we can find that the molecular mass of gas D is 64 grams per mole. With the reactants applied and their atomic masses, copper, 63.5 grams per mole, sulfur, 32.1 grams per mole, oxygen, 16 grams per mole and hydrogen, 1 gram per mole, the most obvious gas with atomic mass 64 grams per mole is sulfur dioxide. With the information that we have so far for experiment 2, we know that the copper has reacted with sulfuric acid to form sulfur dioxide. We know that the sulfur 4+ in the sulfuric acid has been reduced to sulfur 2+ in the sulfur dioxide, therefore, we can suspect that the copper has been oxidized. The copper can be oxidized to copper 1 and copper 2. The copper 1 is usually unstable in aqueous solutions. We can think that the copper 2 forms copper 2 sulfate and this forms a pale blue solution as aqueous copper 2 complex ions, as seen at the beginning of experiment 1. We can conclude that this ion is C. In experiment 3, the filtrate of an excess of copper 2 oxide treated with dilute nitric acid is a blue solution. As in the experiment 2, we can consider that this is the aqueous copper 2 complex ion, meaning that E and C are the same species. The copper 2 from the oxide has not changed its oxidation state. We can guess that the copper oxide reacts with the nitric acid to form copper 2 nitrate. The brown solution formed due to the addition of potassium iodide can be attributed to the iodide in solution, as the iodine 1 ion is oxidized to elemental iodine. The oxidation of iodine 1 ions produces the reduction of copper 2 to copper 1. Followed by the precipitation of white copper 1 iodide, species F. To summarize all, I put in a table the species and their formulas as well as the main reactions. The marking scheme allows also C as copper 2 sulfate and E as copper 2 nitrate. Here are my reaction equations. The marking scheme accepts variations, so you may express them differently than I have here. And this is the end of the question paper. If you found this useful, please click like, and leave a comment, as it will help to carry on making more videos like this.